In this video, we're going to work example problems where we analyze infinite series. So the limit of a series. We're going to be dealing with an infinite series, and we want to analyze, is it convergent or divergent? And if it's convergent, what does it converge to? And remember, what convergent means is that if it's convergent, then the infinite sum actually equals a real number, a finite number. Okay, so for these first few problems, we're given a series, an infinite series like this, and we want to find at least 10 partial sums of the series, graph both the sequence terms and the sequence of partial sums on the same screen, and then see, does it appear that the series is convergent or divergent? If it is convergent, find the sum. If it is divergent, explain why. All right, so I did this, but before this video, in Excel, I worked out 20 partial sums. So let's take a look. So going from n is equal to 1 to 20, here's the a sub n. And so the a sub n is just, you're plugging in the n's into this formula. This is the a sub n, right? The sequence formula. 12 divided by minus 5 to the n. So this is with n is equal to 1, n is equal to 2, etc. Okay, now the s sub n is just, so the sum of the first term. So these two are the same. This is the sum of these two terms. This is the sum of these three terms. This is the sum of these four terms. This is the sum of these 20 terms. Okay, and so in orange, you've got the sequence terms. So the n's are on the horizontal axis, and then this is the a sub n or the s sub n is the vertical axis. So you can see in orange, you start off at minus 2.4, and then as you get into the sequence, it looks like the sequence converges to 0, because we're just at n is equal to 20 here. So imagine going to infinity. It looks like the sequence converges to 0. And then if we look at the series, here's the s sub n's. It looks like these are converging to minus 2. And this makes sense because one of the things we learned in the textbook section is that for a sequence to converge, for a series to converge, the sequence, the corresponding sequence, the a sub n's that you're adding, that sequence must not only converge, but converge to 0, and this does. So if we saw this not converging at 0, converging somewhere else, or diverging, then we wouldn't expect to see the convergence of the series. Okay, now let's do the same thing with this series. All right, here's the a sub n's. Again, we're taking the a sub n formula. Every series, or most series, if a series is you're adding terms of a sequence. Okay, if that sequence, which most of the time it does, the ones we deal with at least, has a sequence formula, then you can think about the series as you're putting that sequence formula into a summation. So this is the sequence formula for this series, and there's the a sub n's with n is equal to 1, 2, 3, etc. And then the s sub n's are just, it's the partial sum. So this is actually the infinite sum here, but if you change this from n to I and you put n here, then that's the partial sum. It's just it depends on, you can represent it however you want. It's just, it's these two terms are equal because we're summing the first term. This, we're summing the first two terms. This, we're summing the first three terms. This, we're summing the first 4 terms. And here, we're summing all 20 terms. Okay, so looking at the graph, here's in orange is the sequence. And it looks like it's convergent, but not to 0, close to 0. It looks like it's convergent to 1. So it's convergent. But since it's not convergent to 0, we expect the series, the corresponding series, to diverge. And it looks like it does. It looks like it diverges to infinity. So this here, going from n is equal to 1 to infinity, we would expect this to be divergent to infinity. Remember, these are the sums. These are the sums. This is the sum of, and it makes sense because if you sum this term and this term, you're like right there. If you sum these 3 terms, you're like right here. You're summing all these. This looks like you're summing 1 as you come out. You're summing 1 each time. So this is like a line with slope 1. Okay, same process. Let's analyze this series. And so the a sub n's, here the a sub n's, it looks like this they converge to 0. The sequence is convergent to 0. Now remember, just because the sequence of a series converges to 0, it doesn't guarantee that the corresponding series is going to be convergent. However, when you flip that, if a series is going to be convergent, then the corresponding sequence must be convergent to 0. Okay, so this is convergent to 0, the sequence. So we say that, okay, there's a possibility that the corresponding series is convergent, and it looks like it's going to be. It looks like it converges to like 1. Now I'm looking at the textbook answer, and it says that that this should converge. It should look like it's converging to 2. And so where are they getting that? Let me extend this to like 100 terms. Okay, so this has like 100 something terms, and it looks like it's converging to like 1.05. So maybe I'm missing something that looks. I think the textbook is saying that it got 2. So I don't know, but you get the idea. This looks like it's converging to something for sure, and it makes sense that it would that the series could converge, since the corresponding sequence converges to 0. Okay, now for each of these problems, we're going to be given a geometric series, and we want to determine if it's convergent or divergent. And if it's convergent, then we want to say what the actual sum is. If it's divergent, then I guess we can try and specify like some things about the divergence, right? Is it going to infinity, negative infinity, oscillating? All right, so we know we have a geometric series. We're working with geometric series. We know we have a geometric series. It tells us. All right, so we know this is a geometric series, and so what we want to do first is find the A1 is 3, and now let's get the common ratio. So the R is going to be, we can say, minus 4 divided by 3. So it's going to be 4/3. So that if we multiply 4 times minus 4/3, you get 16/3. If you multiply 16/3 by minus 4/3, you get negative 64/9. Okay. Now, if we come to here was the sort of summary of we did the analysis on geometric series, and this was the summary of what we found. And so here's a geometric series with the corresponding sequence formula, and the sequence formula would be a little different depending on where you start, like n is equal to 0 or depending on the start point. And you might see the sequence formula for a geometric sequence even for n is equal to 1 in different forms. We're going to, in a few problems from now, we're going to work examples where we start with a geometric sequence and we rearrange it and put it into this form. But for any geometric series like this, and in the textbook video, when we got to this point, I mentioned that, so like here's the infinite sum formula. If the absolute value of the common ratio is less than 1, and I wasn't sure if this formula would be different depending on if you started at n is equal to 0 and I looked into it, and it's not going to be different. If you go and rewatch the geometric sequence video, the algebra video, it's in the calculus playlist, the algebra video on geometric sequences, the overview of geometric sequences, we get this formula here. We derive this partial sum formula. S sub n, the sum formula for any geometric sequence. And if you watch that, you can see that this is independent of like if we're starting at 1 or 0 or whatever. It's just A is the first term, whatever the first term is. If that corresponds to n is equal to negative 50, then whatever. So this is just in general for any, as long as it's a geometric sequence with that common ratio, then this is the S sub n for that sequence, the partial sum formula. And if we take the limit as n goes to infinity of this, well, you can see if as n goes to infinity, if r is greater than, the absolute value of r is greater than 1, this is going to balloon to infinity. And so this entire, this whole thing balloons to infinity, right? Because 1 minus r is a constant, so this just gets huge. If the absolute value of r is less than 1, then as n goes to infinity, this goes to 0. So this goes to 1 minus 0 goes to 1. You're left with a over 1 minus r, which is this. So for any geometric sequence, no matter how it's defined in terms of what's the first term, what's the corresponding n term, what's the first term of the n term, right? So if you started at n is equal to minus 10, then you're going to have r to the, n minus 9 or something like that. Regardless, the infinite sum is equal to if the absolute value of the common ratio is less than 1, the infinite sum is equal to the first term over 1 minus the common ratio. And the partial sum is equal to this, which we derived the partial sum in that geometric sequence overview video. But we didn't take the limit of it as n goes to infinity, and so we're doing that here. That's the idea. If you can find the S sub n for any series, if you can find the partial sum formula, then you're kind of home free as far as analyzing the series, because you can just take the limit as n goes to infinity. You could see if it diverges. You could do the whole analysis, and that's what we in the arithmetic and geometric sequence overview video. That's what we do. We find that S sub n for those sequences. Okay, so the absolute value of r in this case is equal to 4/3, and that is greater than 1. So this is divergent. Now, what we can do is let's be more specific about the divergence. What kind of divergence is this? Is it diverging to infinity or negative infinity? No, because what we talked about was that since this is negative, what's going to happen is it's alternating. So as n goes to infinity, the alternating, it wouldn't be a problem if this was less than 1, because you'd be adding a very tiny positive number and then subtracting, adding a very tiny negative number. But since this is the absolute value, this is greater than 1, as n gets large, you're going to be adding a huge positive number, then subtracting a huge negative number, however you want to, I don't know if I'm saying that right, but the partial sum is going to be doing if you have n is equal to 5,000, you'll have a point up here, then a point down here, because the next term is subtracting a huge number. So it's going to be this is going to be oscillating divergence. So it's not going to diverge to negative infinity or positive infinity, right? You see, this is just the fourth term. These numbers are getting bigger. 64 divided by 9, and so the magnitudes of these numbers are just going to get bigger and bigger and bigger. But you can see you're going to be alternating. It's not going to be like the partial sum's not going to be just continuing off to infinity. Not when you subtract some huge negative number. Okay, same type of problem. We know that they tell us this is a geometric sequence. So the first term, we'll just say A is 10, and then the common ratio is going to be minus 2. Okay, now the absolute value of r here is less than 1. So we expect this. So that means this is going to converge. If they're telling us, we don't need to check. If we've already proven that if we know we have a geometric sequence and that common ratio, the absolute value of it is less than 1, it converges. And the infinite sum, the sum of the infinite number of terms of this sequence is going to be equal to an actual value. It's going to be A over 1 minus r, so 1 minus 1/5. So 1 plus okay, 5/5. So 25/3. That's what this is equal to. Okay, same type of problem. They tell us this is a geometric sequence, and we can say, so the r is going to be 1/2 divided by 2. 1/2. Okay, so the absolute value of r is less than 1. So we know that this series converges. One minus 1/4. Eight thirds. This infinite sum is equal to 8/3. And also note, so this was alternating, right? An alternating geometric sequence. That doesn't, when it comes to thinking about the infinite sum of a geometric sequence or geometric series, that doesn't matter. The fact that it's alternating doesn't come into play. Okay, so we want to find we want to see if this is, they tell us this is a geometric sequence. And so do we need to rearrange the terms? It doesn't look like it. A times r to the n minus 1. So no, it's already in this form here. And so, well, it's not about being in a certain form. It's more about just being able to identify what is the first term. So when we're starting at 1, so we plug in 1, we get 0.73 to the 0 power. So we see that A is equal to 12. And then we can see what the common ratio is just right there. All right, so absolute value of R is less than 1. So this is going to be, this series is going to converge. So 1 minus 0.73. So 12. $44.4. I mean, let's try and do the exact answer. So, okay, 73 over 100. So, okay. So, all right, so all right, 12 divided by 3 is 4, 27 divided by 3 is 9. So, yeah, there we go. Let's give the exact answer. So this is equal to 400 over 9, right? It's pretty cool. This infinite sum here is equal to 400 over 9. Okay, so with this, you know, we want to put it into this form, but it's really for what we're trying to do here, just to get to analyze for convergence or divergence and get the infinite sum if it converges. We're just trying to find what is the first term and what is the common ratio. And with this form, it's easy to pick those out. So, you know, we could get the first term by just putting in n is equal to 1. But I mean, let's try and rearrange this. Let's put it into that form. That it was, what was it? A r to the n minus 1. Let's put it into that form. So we've got minus 1 to the n minus 1 times, okay, now we've got minus 1 to the n minus 1 times 3 to the n over 4 to the n times 3 to the minus 1. Okay, so you've got minus 1 to the n minus 1 over 3 times, okay, so we can see the common ratio is going to be 3/4 or minus 3/4. I mean, let's try and get this minus sign back in here. So, all right, if we can do this for sure. Okay, now let's say we made this n minus 1, and that would work as far as, so when in this formula, if you agree we haven't changed the equation here, when n is equal to 1, this is positive. The whole term is positive, and that's the case here. When n is equal to 1, positive. So the alternating is correct here. The alternating is correct. However, when n is equal to 1, what does the term equal to? Because it doesn't, this doesn't go away. Like this 3/4 doesn't go away. So this is positive 1/3, and then this is 3/4 to the 1. Okay, so the first term is 1/4. So we want to put a 1/4 here. Now we haven't changed the summation. Okay, so now with this, we can say that A is equal to 1/4, R is equal to minus 3/4. So the absolute value of R is less than 1. So this is going to converge, and it's going to converge to so we've got 7/4. 1/7. This and this is equal to 1/7. Okay, so they're telling us that this is a geometric sequence, so we just need to figure out what's the first term and what's the common ratio. And so we could get the first term easily by just plugging in n is equal to 1. Let's do that just to show you. So when n is equal to 1, you've got e squared over 6 to the 0. So just e squared. Now, the common ratio is not, I mean, I don't know, maybe e divided by 6? I don't know. So we can write this as, so e to the n times e to the n, 6 to the n, 6 to the minus 1. Okay, so, and then we would have 6. Okay, well, we could do, so, okay. So this is based on properties of exponents. So if you have a, b to the n, that's a to the n, b to the n. And so this would be e over 6 times e to the n. E squared over 6 to the n. And so there's the common ratio, e squared divided by 6. Well, we know the first term is e squared. So what we've got is e squared right? Because this is the form that works that way, where if you have to the n minus 1 power, the common ratio, you just put the first term out front. Because when n is equal to 1, at least for when you're starting at 1, because when n is equal to 1, this goes to 1, and you're left with the first term. Okay, so there we go. So again, a is equal to e squared. Now, what is e squared divided by 6? Is that... that is not greater, the absolute value of that is not it's greater than 1. So this is going to be divergent. But the common ratio is positive, so this is going to diverge, but we can put infinity.